Hello, and welcome to this session on understanding and using the Geostationary Lightning Mappers. My name is Joseph Patton. I'm a faculty researcher and meteorologist at the University of Maryland, and this is in support of the GOES-R Datajam 2023. For the first part of this training session, we'll talk about how the GLMs work and which products that they create. So, first of all, what is the Geostationary Lightning Mapper? Well, the Lightning Mapper, or GLM, is an instrument on board the GOES-16, GOES-17, and GOES-18 satellites. This instrument observes bright flashes of light from the atmosphere at a specific wavelength associated with lightning. These observed changes in lightning behavior give insights to forecasters from what the severe threats from thunderstorms will be. And lightning flashes from the GLM are processed into gridded products to quickly convey information to forecasters and researchers, information about the lightning's characteristics, such as the number of flashes and the size of flashes. So how do the GLMs detect lightning flashes? Well, bright optical sources of light are observed with an imager on board the GOES-16, 17, and 18 satellites with a very narrow wavelength corresponding to lightning emissions. Sources are observed every 2 milliseconds and are then compared with a background image, which is updated every 2.5 minutes. So the sources that are bright when compared to that background image count as an illuminated pixel or an event. So each individual pixel that is illuminated past the detection threshold on each 2 millisecond frame is labeled an event. Those events are then combined into groups of simultaneous adjacent events. And finally, groups are combined into flashes by combining one or more sequential adjacent groups. The field of view of the two GLMs, goes east and goes west, stretches across most of the western hemisphere, as seen in the image in the right corner. This short video gives an idea of how to visualize how the GLM is creating gridded products of lightning flashes from thunderstorms. Lightning branches are complex and can be in many different shapes, but when viewed from above, these lightning channels can be mapped by their spatial extent of the flashes. The GLM observes those flashes from geostationary orbit, and they can classify the lightning by using 3 different gridded products. Those are flash extent density, which shows the flash counts, minimum flash area, which shows the size of the smallest flash, and total optical energy, which shows the accumulated brightness from all the flashes. To go over those gridded products one more time, there are 3 products which are created from the GLM, which are produced each minute as level 3 data. These products are flash extent density, or FED, which shows a count of how many flashes are coincident within each GLM pixel, which is about 8 kilometers by 8 kilometers. The next is minimum flash area, which is the area in kilometers squared of the smallest flash within any given pixel in which a flash was detected. So if there are multiple flashes covering the same pixel, it will find the area of the smallest flash that covered that pixel and display the area of that value in that grid cell. The smallest minimum flash area values will be 64 kilometers squared, which is 1 GLM pixel, 8 kilometers by 8 kilometers. Finally, there's total optical energy, or TOE, which shows the amount of optical energy in femtojoules, or joules times 10 to the minus 15, which is received by the GOES satellites. Looking more specifically at flash extent density, we can see that the higher flash extent density values correspond to more lightning flashes, and that increase in lightning flashes or increase in lightning activity typically indicates stronger or strengthening storms. In the imagery on the right corner, cool colors or blue colors indicate lesser flash counts, whereas warm colors such as the yellows, oranges, and reds indicate relatively larger flash counts. This example shows a squall line, which is a line of strong thunderstorms all moving in one direction, and it quickly shows which sections have more lightning activity and therefore might be more likely to lead to severe weather. We can see that there are generally higher flash counts in the northern section, and in addition, jumps in lightning flash counts have been shown to correlate closely with greater potential for severe weather. So if a storm suddenly starts producing many more lightning flashes than it was prior, that could indicate an increased potential for severe weather. The minimum flash area gridded product again, shows the smallest flash within any given pixel in which a flash was detected. Contrary to what you might think, smaller flashes actually indicate strengthening convection, whereas larger flashes might indicate weakening convection. The reason is that in the strong updrafts at the center of a storm, you have a lot of charge separation happening very quickly in a small amount of area. That leads to many more smaller flashes in the strengthening updraft of a thunderstorm. And these many more smaller flashes show up as smaller values in minimum flash area. Minimum flash area goes down to 64 square kilometers, as we've said before, and those are represented by the gold pixels in the imagery in the right corner. Minimum flash area has replaced the average flash area product, as it is more indicative of the smallest flashes. Storms or sections of mesoscale convective systems which are strengthening can be quickly identified by those yellow and green pixels indicating smaller flashes. Likewise, storms which are weakening might be identified by the purple and blue pixels, indicating that the flashes are growing larger in size. You might see, however, on the back side of this squall line, there are some large areas showing purple MFA values, or very large MFA values. And those areas represent strong cloud-to-ground flashes behind the line of the most active thunderstorms. And those strong flashes can actually be a particularly dangerous event for public safety, as they occur after the main line of thunderstorms, and they typically indicate a large amount of charge being conveyed to the ground. Finally, looking at the total optical energy product, or TOE, we can see that it shows where there are brighter flashes, which may indicate more energetic flashes, which may indicate stronger or more numerous thunderstorms. Brighter flashes, higher TOE, are sometimes associated with storms which are strengthening, but not always. Forecasters in practice have found that there is a less clear relationship between TOE values and the indications of how storms will continue to form. Other GLM gridded products such as FED and MFA, as well as ground-based lightning networks, should be used to confirm the lightning activity and build a conceptual model of how thunderstorms are evolving. To talk a little bit about GLM data quality, we can see that the detection efficiency of the instrument is greater than 70% when averaged over the full disk and over the 24 hours in a day, and that detection efficiency increases at night greater than 90% when we're comparing sources of lightning against darker backgrounds. The detection efficiency decreases near the edge of the field of view of both GLM instruments and goes east and goes west as pixel sizes increase. And likewise, detection efficiency increases towards the nadir or the center of the field of view of both GLM instruments. The false alarm rate, or FAR, is less than 5% when averaged over the full disk and over the full 24-hour day. False alarms can be caused by many things, such as sun glint, which is sunlight reflecting over waters, as well as there are some artifacts which can be manifested within the GLM data itself. The bar artifact represents a line of non-physical lightning flashes, which in this case we can tell are not physical because of their abnormally dim appearance in total optical energy. But there are other false alarm examples, such as solar farms and bolides, which are meteors exploding in the atmosphere. Recent filters have significantly reduced the number of false alarms, so they are less of a worry than they used to be. To summarize Part 1, the Geostationary Lightning Mappers, or GLMs, cover much of the Western Hemisphere with a significant overlap region over the central United States. The GLMs produce 3 gridded products as their level 3 data files. Those products are flash extent density, minimum flash area, and total optical energy. Flash extent density, or FED, represents the count of the number of flashes within each pixel. Minimum flash area, or MFA, represents the smallest area of any flash detected within each pixel. And total optical energy, or TOE, represents the total amount of optical energy or brightness detected within each pixel from all lightning. The detection efficiency of the instrument is greater than 70% when averaged over the full disk and 24 hours, and that detection efficiency increases at night when there are dark backgrounds. Part 2 of this presentation will focus on GLM applications and selected GLM case studies. There are many GLM application areas as listed in the table on the right-hand side. One of the most important GLM application areas is lightning safety. The GLM is a unique instrument that shows the entire flash footprint of a flash, while ground-based sensors often provide just point sources. This allows forecasters and responders to see the entire spatial coverage of lightning flashes, including where lightning strikes may be affecting other resources that are not shown by these point sources. One example of a very large lightning flash came here from the Jacksonville Jumbo Shrimp, and this is from after one of their games where they're showing fireworks, but then also there's a large flash that occurs right there. And we can see that flash has a large flash footprint that's not defined just by where it touched ground, but by a much larger area, which could be affecting life and property. Another very important GLM application area is improving severe thunderstorm and tornado warnings. The GLM observations increase confidence in forecasters, as they are another tool in the toolbox for assessing the increasing severe potential for thunderstorms based on its lightning activity. The imagery here on the left shows flash density as well as National Weather Service warnings for severe thunderstorms in yellow and tornadoes in red. And we can see increased flash counts toward the northern part of the line where there are more numerous severe thunderstorm warnings. Getting into our first case study, this is another squall line, a line of strong thunderstorms moving through the central United States, particularly in the state of Nebraska. The question here is, what do the GLM products show about this system? Is there a preferred region for severe weather to continue? We have minimum flash area in the center, and on the left we have flash density, and on the right we have total optical energy. The answer here is that there was a portion of the squall line near Lincoln, Nebraska that had higher flash counts, indicating increased potential for severe weather. This resulted in an EF2 tornado, which destroyed several well-built barns and grain silos. Our second case study here is from a hurricane. This is from Hurricane Dorian in 2019, and what's being shown here is flash extent density in the blue, yellow, and orange colors, as well as the GOES 16 Channel 2 visible IR imagery, which is shown in the grayscale colors underneath. So the question for this case is, what is flash extent density showing here? Based on this satellite imagery, would you expect Hurricane Dorian to weaken, strengthen, or stay the same intensity? The answer in this case shows that increasing flash extent density, or FED values, could indicate the strengthening of the eye wall, or the inner core, of Hurricane Dorian. Looking further into the Hurricane Dorian case, flash extent density shows a large increase in the number of lightning flashes, and that large increase in lightning was associated with a burst of convective activity within the eye wall of Hurricane Dorian. Significant strengthening was observed after this lightning activity increased, as maximum sustained winds, according to the National Hurricane Center, increased from 150 miles per hour to its peak intensity of 185 miles per hour as it made landfall in the Bahamas. Finally, we're going to look at a case of a marginally severe storm where the lightning flash counts were relatively low, but severe weather still occurred. In this section, we want to hammer home that flash extent density, minimum flash area, and total optical energy work better together, along with other satellite and ground-based observations, to have the most complete picture of how thunderstorm activity is evolving. This is an example of summertime afternoon thunderstorms in the mid-Atlantic in Maryland. And in this case, as we play the flash extent density animation, we can see that the number of flashes increased. We have these light blue colors, and that prompted this severe thunderstorm warning, which is shown in the yellow outline. So did this warning verify? Was this warning warranted based on the number of flashes that were increasing at the time? And the answer there is yes. During the severe thunderstorm warning, 2 reports of severe weather came in of large trees down over roads near Baltimore, Maryland. These severe weather reports corroborate the increased severe potential that was shown by the increasing number of flashes within the GLM, flash extent density. Looking at this same case from the perspective of minimum flash area, we can see, especially at the beginning, although the flash counts in FED started off relatively uniform, we can see that there is a strong core of the thunderstorm already building, as these gold MFA pixels represent the center of the strong updraft. As the thunderstorm develops, that strong updraft also develops with even more minimum flash area values. But as those minimum flash area values increase, representing a potential weakening of the thunderstorm itself, we can see that the severe thunderstorm warning was then allowed to expire. And that coordinates well with the GLM showing a decreased potential for severe weather as those minimum flash area values increase. In summary, the GLM gridded products, flash extent density, minimum flash area, and total optical energy provide valuable insights into lightning activity and thunderstorm evolution. Increased flash counts and smaller flash areas typically indicate strengthening storms. Using other weather observations such as visible satellite, along with all the GLM gridded products together, can improve confirmation and provide a better understanding of lightning activity. If you have any questions or comments, feel free to email me at the email that's shown on the screen, or come see me in my office hours on Monday, October 2nd from 2 p.m. to 4 p.m. Eastern Time. Thank you very much for listening, and good luck.